Good morning. I welcome you all to this session of fluid mechanics. Well, last class we just started translation, rotation and deformation. We just tried to recognize these three terms that in case of a fluid flow, the three distinguishable features of its kinematics that are translation, rotation and deformation. We also recognize the difference with the motion of a solid, that where for solid bodies, all the particles within the solid move with the same velocity. For liquid, for fluid, the particles constituting a fluid body move with different velocities. That is the basic difference between the motion of a solid and a fluid body. So in respect of that, the three distinct features come in the course of fluid flow: translation, rotation and deformation. Now let us see that in case of a motion described like this, where let us consider a two-dimensional case. Sorry, this is y. If you take two-dimensional system in xy axis, if we consider the u component of velocity, that is in the x component, and v is the y component velocity. So u is constant. That means u and v doesn't vary with the space coordinate. Now in this context, I like to tell you the translation, rotation and deformation are the result of the variation of velocity components with space coordinates. So fluid may be steady or unsteady. If it is steady, all the pictures correspond to all times, or if it is unsteady, the picture corresponds to a particular instant. So therefore, regarding the variation of velocity component with space coordinates, let us consider a very simple case, that is a uniform flow. U, v, both the velocity components are constant. We consider a two-dimensional case. In that case, what happens? If we just recognize a fluid element, whose lengths are delta x, let the element is, and the lengths are delta x and delta y. The element is A, B, C, D with the lengths delta x and delta y. What will happen in course of this flow field? This will be simply translated like this. This will be simply translated like this. That means this will be the position, respective time, different times, this will be the position. This will be simply translated. That means the fluid will be simply translated along the resultant velocity. Now what happens, since u, v are constant, so each and every particle or point in this fluid element A, B, C, D will move with equal velocities in x and y direction. That means the length delta x, delta y, that means here if we consider this is A, B, C, D, it has come here, the length delta x and delta y, that means this length will remain unchanged, delta x and delta y. That means if we consider the movement for a unit time here, then if A moves by a distance u, that is the x component of velocity, b, this point also moves by the same amount u. Similar is the case for movement in the y direction. You understand? That means if this A moves, that means this distance is v, considering an unit time, then D also moves by the same distance v. That means each and every point moves with the same velocity and their displacements are same, so that the sides are not changed in course of motion, and also all the sides move parallelly. That means AB comes here parallel, AD, BC, they are parallel. This is simply known as translation. This happens in case of a solid body. If solid body is given a rectilinear motion, displacement, the solid body displaces like that. That means none of its sides are changed, altered, and the sides are translated parallelly. The displacement takes place so that the angle, included angle between two linear segments, remains unaltered. This case is known as pure translation, or sometimes we tell as translation. This is known as pure translation when u, v are constant. That means the entire flow field is invariant with the space coordinates. All right? Okay, I think you have understood, all of you. Now next consider another simple case where just we take little, this was earlier one is the simplest case. Now we give little restriction. That means let us now consider a situation where u, x component of velocity, y component, is a function of x only and v is a function of y only. That means we consider the variation of the velocity components with the coordinate axis, but take a very special case, that is x component of velocity varies with x coordinate only, while the y component of velocity varies with y coordinate only, which mathematically means that del u del y is 0 and del v del x 0. But this mathematics does not have much bearing now with the physical understanding. Just to write, for the sake of writing, I write this, that u is a function of x and v is a function of y. If we take a special case like that, then let us see what happens in course of motion of a fluid element A, B, C, D, for example, the A, B, C, D, where this length was delta x and this length is delta y initially. What happens? So if we see at a later time this be the position, what we will see now, first of all let us recognize one thing, that when u is a function of x, that means each and every point, for example in the linear element AB, which is varying with x coordinates, move with different u velocities, which means B has an opportunity to have a displacement relative to A in the x direction. This is because the B point has a velocity more than u. For example, if u A point more than A point has a velocity u, at the point B the velocity will be u plus del u del x into delta x. So B has a higher velocity. So by this AB linear segments get elongated continuously. Similarly, since the V component of velocity varies with y, which means that each and every point on the linear segment AD which are varying with y coordinate had a different y component velocity, which can be told in this way that D point has the opportunity to have a relative displacement over A in the y direction. So for this type of velocity variations gives a continuous elongation of the linear segments. But another interesting fact is there, because of this simplification, that u is neither a function of y, v is neither a function of x. In that case what happens, that if we now consider the different points in the linear segment AB, so one thing is true, at all points y component of velocity is not changing. This is because v is not a function of x. This is 0, because all these points vary only in the x coordinate. So for these reasons the line AB gets parallelly shifted. Similarly, the x component of velocity for all the points on the linear segment AD does not vary, because x component of velocity is not a function of y, which means that the line AD shifts parallelly. So as a result of which what happens, there is a elongation of this element in the linear directions without, let this is the earlier one, without changing. It is really exaggerated too much, because the elongation will be lower than the smaller than the original length. However, for understanding there will be no difficulty. So therefore A, B, C, D without any change in the included angle. That means the sides move parallelly but with a linear elongation. Obviously, if we take this picture, that means this displacement per unit time, this position after an unit time, so we can tell that this elongation is what? It is very simple, because if A moves by an amount u per unit time, so B will move by a distance, this distance will be u plus del u del x delta x. That means per unit time A will move to a distance which is the velocity here, B will move to a distance what is the velocity at B. Because of the variation of u with x, the velocity at B will be u plus del u del x del x. Therefore the elongation, this part in x direction, or displacement of B with respect to A in x direction, will be del u del x delta x. In the similar way, if you see the A, if the velocity here is v, y component, so A moves, that means the displacement of A per unit time is v, whereas the displacement of D per unit time will be more than v, that means this displacement, it is v plus del v del y delta y. Why? This is because if v is the velocity at A, then the velocity at D will be, because of the variation of v with respect to y, will be v plus del v del y dy. This is the velocity at D. So, D will move by this amount. So, therefore, we see that this displacement or elongation in the y direction is del v del y delta y. I think this picture is clear, but the sides are displaced parallelly. There is no change in the included angle. This is because u is not a function of y, only x, and v is not a function of x, only y. Now, in this case, we define a terminology, rate of linear strain or linear deformation or linear rate of linear deformation. Why? There is a linear deformation in this case. So, we see that in this case there is a linear deformation because these sides are linearly deformed or linearly strained. So, there is a linear strain and linear deformation without any change in the included angle. Shape of the body remains unchanged, and rate of linear strain or linear deformation is defined as the rate of change of the length per unit time. So, per unit time, this is the change in the length in the x direction. So, therefore, rate of linear deformation in x direction, it is symbolized as epsilon x, that means in x direction with a dot usually is recommended because it is the rate, is the change of displacement in the x direction per unit time, per unit length. So, per unit time, this is the elongation in the x direction for a linear segment in x direction divided by its original length. That means simply del u del x. Similarly, epsilon y is del v del y delta y. That means this is the elongation or strain or deformation per unit time in the y direction divided by its original length. So, del v del y. So, this can be written for in general for a 3-dimensional flow, del u del x epsilon y dot is del v del y and epsilon z dot is del v del w del z. Therefore, we see that when in a general 3-dimensional flow, if the component of velocity is a function of that space coordinate, that means x component is a function of x coordinates, that means del u del x is non-zero. Similarly, v is a function of y, so that del v del y is non-zero, it exists. Similarly, w, the z component of velocity, is a function of z only, so that del w del z is non-zero. Then a fluid body gets simply elongated in the linear direction, that means all the sides in z direction also sides will be elongated. This is the rate of linear deformation, that is elongation per unit original length per unit time. But the shape of the body will remain unchanged, since the u component of velocity is neither a function of y and z, v component of velocity is neither a function of x and z, and w component of velocity neither a function of x and y. So, this is another simple case. Now, we come to the most general case, you can now appreciate very much what is that general case, that where u and v in a 2-dimensional frame of reference both are function of xy, because there is no need of considering u is a function of x and v is a function of y. In most general case of 2-dimensional flow, 2-dimensional flow means where the velocity components are functions of only 2 space coordinates and we consider only 2 velocity components. This is the definition of a 2-dimensional flow. So, where in a 2-dimensional flow, the most general case is that 2 velocity components u and v should be function of both x and y. In this case, what happens? In this case, it is very simple to recognize that if there is a element a, b, c, d initially in this shape with delta x, that is AB, length AB, and if we define this length AD as delta y, that means a rectangular fluid element of delta x, delta y. Now, what happens that since u is a function of y along with the function of x, what happens if we consider different point on the linear segment AB, it is not only having a velocity different u component of velocity, it is having different y sorry, it is having different y component of velocity, obviously, because v is a function of x now, for which now we can say that each and every particle on the linear segment has got a relative displacement over any particle here, for example A, both in x and y direction. That means now we can tell that if this is the velocity u at A, the velocity u at B will be u plus del u del x dx. Similarly, the y component of velocity v at A, so y component of velocity at B will be v plus del v del x dx, which means now B has an opportunity to have a relative displacement over A in both x direction and y direction. So because of this relative displacement in y direction, line AB will be tilted like that. So it will not move parallelly. Similarly, if we consider the line segment AD, you see clearly that because of a change in v with y, so it will be linearly elongated as we have discussed earlier. But since u is a function of y also, that means this direction velocity for all elements, particles on AD will be different, because u is now a function of y, for which the point D has got an opportunity to have a relative displacement over A, not only in the y direction but also in the x direction, which means then the line AD will not be parallelly shifted, so AD will get a tilt. Clear? So therefore, the situation is like this. Let us consider this is the old one. Now this is the situation. So therefore, A, B, C, D. Now you see there is the distortion in the shape. It is clearly understood. Now obviously from our discussion we can tell that this is what? This is del u del x, the linear elongation in the x direction. So this point B has got a relative displacement over A in x direction is this one. So what is this one? Please tell me what is this one? Del V, please, del V del x delta x. Very good. This is because this relative displacement of B with respect to A per unit time, that means if you consider this position after unit time is nothing but the extra velocity V which the B point has over A, that is V plus del V. That means if A moves with a displacement per unit time V, then this B point will move. That means if I take a projection here, this will move by this value. That means V plus del V del x dx, because this has a higher velocity in the y direction with respect to A by this amount. So this will be the relative displacement. Very good. Similarly, in this direction, obviously if we take a projection, this displacement, as we know, this is the linear deformation, that is del V del y delta y. Similarly, what is this value? This value will be, this is nothing but a displacement of d with respect to A in x direction, and this is responsible for del u del y delta y. Del u del y delta y, because it is a change in u velocity over a change of length delta y. Now if I denote this angle as alpha and this angle as beta, well, alpha and beta, now here many terminologies have to be defined. First we define the rate of, these are the terminologies you have to know, rate of angular deformation, rate of angular deformation, or sometimes we can tell shear rate. Many names are there, or rate of shear deformation, shear deformation. So these are the terminologies, the rate of angular deformation, rate, shear rate, or rate of shear rate or rate of shear deformation of a fluid particle at any point we define. How do you define? Definition is very important rather than the different terminology. Rate of angular deformation or shear deformation at any point is defined as the total rate of change in the total angle between two linear segments of a fluid element which were initially perpendicular. That means if this be the definition, that means it is the rate of change of angle between two linear segments of a fluid element which were initially perpendicular. That means if we consider AB and AD two linear segments of a fluid element which were initially perpendicular. So, the per unit time the change in its angle is alpha plus beta. So, therefore, the rate of angular deformation or shear deformation is alpha plus beta, and this is symbolized as gamma dot xy. Gamma is the terminology or nomenclature for this, dot is for the rate, and xy is given because this deformation is taking place because of a tilt of the linear segments. So, this happens only in the xy plane about the z axis. In case of a 3-dimensional flow, there will be a deformation of the surfaces in the other plane yz or xz plane. So, therefore, this plane specification is given gamma dot xy. In this case only one plane, because this is a 2-dimensional case, it has got only one plane. So, in this case it will be gamma dot or gamma dot xy, you can write alpha plus beta. Now, from a simple geometry you see that in this triangle AB, let us give some name A dash, A dash B is a school level. So, tan alpha we can write, you see tan alpha is what? This divided by this length, A B A dash divided by A dash, tan alpha. All right, I think tan alpha you understand, A dash B divided by, that means tan alpha becomes equal to what? Del V del x delta x divided by delta x into 1 plus del u del x. All right. Similarly, we can write tan beta is equal to del u, del y times delta y divided by delta y into 1 plus del v del y. Now, for small angles alpha and beta, this deformation small, considering this small, we can write alpha is equal to tan alpha. As you know, for small angles, the angle tangent of the angle equal to the angle itself, tangent and sine of the angles become equal to the angle. From the series you can appreciate that. So, therefore, we can write alpha plus beta is equal to gamma dot xy is equal to what? This plus this. That means, if I write this plus this, okay, let me write is equal to del v del x delta x divided by delta x 1 plus del u del x plus simply this quantity del u del y delta y divided by delta y. Now, considering these values to be small, that means the angles are small, strain rates are small, we can neglect the higher order term product of these two, so that if we make a simplification, we will simply get del v del x plus del u del y, del v del x plus del u del y. So, therefore, we get the shear rate or the rate of angular deformation in xy plane is simply del v del x plus del u del y. All right. Now, we appreciate, okay, all right, del v del x plus del u del y. This you can see at home also, this we product we neglect. So, ultimately this will be del v del x plus del u del y. Okay. Yes. So, everything will be this, you take this way you cannot find out, you take this 1 plus del u del x to the power minus 1, 1 plus del v del y to the power minus 1, expand it and neglect the higher order and find it. It is very simple mathematics, you have to follow it. All right. So, this becomes del v del x del u del y. Now, again this is the final picture, the most general picture, we will be finding so many things from here. Now, again with respect to this picture, apart from rate of angular deformation or shear rate, another concept comes, that is rotation. What is meant by rotation of a fluid element? So, when a fluid body is deformed like this in course of its motion, because of a very general case when the velocity components are function of all space coordinates, then the fluid body deforms like this. We define two quantities, one is the rate of angular deformation, another thing which is defined is the rotation. Now, we have to know what is this. So, rotation at any point is defined as the average angular velocity of the two linear segments which were initially perpendicular. Just like this, it is the rate of change of angle which is the deformation it is other way, it is the average or arithmetic mean of the angular velocities of two linear segments. Now, when this AB gets tilted like this, that means it has got a rotation sense is coming, that means it has got an angular velocity about A at A about the Z axis. Similarly, as AD is shifted like this, not parallelly, that means it gives a concept of angular velocity about Z axis at A. That means while the line AB has an angular velocity in this direction, line AD has got an angular velocity in this direction. So, in that case, if alpha and beta are the angles made per unit time, as we have found out, otherwise we cannot tell the displacement like del u, del x, del v, that means I have considered per unit time. Then we can tell the angular velocity is alpha for this AB, and for this AD angular velocity is beta, that means the angle made per unit time. But velocity is a vector, that means this should have a sign or sense. If we take a conventional nomenclature, as which one we will take as anti-clockwise, if we take, which is usually taken as the positive, that means alpha is positive, beta is negative. So, therefore, from this we can write that the rotation is defined with omega about the z axis for the point A is half of the alpha plus beta, alpha plus beta, alpha plus beta. So, what is alpha plus beta? So, if you write this half of alpha beta, that means alpha is the half of this plus this, which becomes equal to, as I did, half del v del x plus, sorry, minus, because beta is minus. So, I write half alpha minus beta with the minus sign, del v del x minus del v del x minus del u del y. So, therefore, we see the deformation rate in the xy plane is del v del x in a two-dimensional case, del u del y. In a two-dimensional coordinate system, that means x and y, where u and v component of velocity varies with both the space coordinates, the most general case, that is x and y. In that case, a fluid body has got a rate of angular deformation in the xy plane, which is given by del v del x minus del u del y. Sorry, del v del x plus del u del y, very good, sorry. And fluid body has got a rotation about the z axis at any point, which is given by half del v del x minus del u del y. All right. So, this is the concept. Now, in a three-dimensional case, if we consider, now before that, of course, I like to tell you some special cases. Let us consider some special cases. Special case. What is that special case? Let us consider, now we can make many special cases. Let us consider this special case when UV variation is such that del u del y, let del u del y is minus del v del x. Let us take that u is a function of xy and v is a function of xy in such a way that del u del y is minus del v del x. So, if this take this special case, then what happens? Just you think that this is the xy plane, then what happens? Let us consider this as the body here, just at the same place we consider, we are not going somewhere else. Then what happens? Del u del y is del v del x, you will see this thing will happen. The included angle will remain same. Why? This is del u, del v, del x, delta x. Let this is delta x. A, B, C, D. A, and this is the dotted one is the final position. Now, I want to show that if del v del x and del u del y are same in opposite sign. Now, earlier what we did? We considered, please see, del u del x, now del v del x and del u del y are in the same direction, same sign. That means here what happened? The del v del x is positive. That means v increases with increase in x. That is why B has got a displacement over A in the positive x direction. Similarly, here we have considered the most general case of del u del y positive. That means the u velocity increases with increase in y. That means D has got a displacement in x direction over A in its positive direction, that means this one, so that the sides have been displaced like that. But if we consider now, for example, del V del x is positive, that means the V component of velocity increases with the increase in delta x. So B has got a relative displacement over A in y direction, in this direction, that is positive y direction. Now if I consider the del u del y is minus, that means if it is positive, del u del y is negative, that means D will have a displacement in the x direction, less displacement over A, that means in other way we can tell that it has got a x direction displacement in this direction. So therefore we can tell that the particle will move in this way, that means in the same direction the linear element will be rotated, and since they are equal in magnitude, that means alpha will be equal to beta, alpha will be equal to beta, because if these two are same, if you recollect, alpha is del V del x divided by del x, we can write that if we neglect this next term, the del x, that means it is del V del x, and beta will be del u del y. So that means that this del u del y and del V del x terms, if they are in opposite sign but equal in magnitude, then what happens, both the linear elements will move in the same direction, and moreover when they are equal, what happens, the included angle remains same, that means this is the earlier included angle and this is the final included angle, both of them remain 90 degree. This type of rotation is known as, this type of motion is known as pure rotation, or more easily understood or conceptually solid body rotation. Solid body rotation means the rotates as a solid body, this is solid body rotation. So this is solid body rotation, that means solid body rotates like that by making the included angle same. So this is known as solid body rotation. If we consider another special case where del u del y is equal to del V del x, that means they are equal and equal in sign. In that case, from the definition, gamma dot xy becomes 0. Sorry, gamma dot xy is not become 0. Here the gamma dot xy becomes 0. I am sorry, please come to this. Here what happens, this is a solid body rotation and pure rotation. Now what are the values I see? Gamma dot xy is del V del x, sorry, plus del u del y. Here gamma dot xy is 0. And here one find out the omega dot z, it is half of del V del x minus del u del y. That is del V del x is minus del u del y, or del u del y is minus del V del x. That means it is either del V del x or equal to minus del u del y. Obviously, this is just like the solid body rotation where the rate of shear deformation is 0 because there is no change in the included angle. So therefore, for a solid body rotation or pure rotation, there is no angular deformation. So this value is 0. And angular velocities, arithmetic mean of the two linear segment is nothing but the angular velocity of the body as a whole, which is del V del x, either del V del x or del u del y. Very simple. So we can understand what is meant by solid body rotation and the solid body or pure rotation, where the rate of angular deformation is 0 and angular velocity exists and it is given by this value. But now take a special case where del u del y is del V del x. In this case, gamma dot xy is not 0, it is either twice del V del x or twice del u del y. But in this case, by definition, omega dot z is 0 because this is equal to this with the same sign, so omega dot z, that means rotation is 0. What is this situation? This situation is very simple to conceive, x and y direction. Let us consider the initial particle like that, element like that, A, B, C, D. A final one will be like this, okay, where this alpha is equal to beta. They are of the same sign. That means if del V del x is positive, this is del V del x, if this is del x. So del u del y is positive also. That means in the positive direction there is a displacement. So it is del u del y is also positive. So therefore both of them are in the same sign. So the two linear elements will move in the opposite direction. So if two are negative, then this was moving in this direction, this was moving in that direction. That means both of them will be moving in the opposite direction, which we first considered in general case. In that case what happens, the alpha is equal to beta. That means the angular velocities of the two linear segments initially perpendicular will be same, but will be in the opposite direction. That is why by definition of the rotation, the arithmetic mean becomes 0. So rotation becomes 0, but it has got definitely a shear deformation or angular deformation, because the rate of change of angle is alpha plus beta, or 2 alpha or 2 beta. So this either by this or this. This type of motion is known as irrotational motion, irrotational flow or motion. So now we see that we have recognized 3 distinguishing features, that is translation, deformation and rotation. Now let us write in case of a, after this physical understanding, that in case of a 3-dimensional system x, y, z, we can write epsilon dot x. Now terminologies are known, that is the rate of linear strain is del u del x, and you consider u as a function of x, y, z. What is u? X component velocity. What is v? Y component. What is w? Z component. So v as a function of x, y, z, and w as a function of x, y, z. So now epsilon dot is del u del x, epsilon dot y is del v del y, and epsilon dot z is del w del z. This defines the linear strain rates in 3 directions. That means 3 sides elongates in this way. Now omega dot x, that means about x axis, omega dot y and omega dot z. Omega dot z we have already recognized half del v del x minus del u del y. In defining, so what we have considered? We have considered the anticlockwise direction rotation or angular velocity is positive. Similarly, with respect to x direction, you see which one will be positive? Anticlockwise rotation. That means in this direction rotation, and this direction rotation will be responsible by the z component of x component of velocity in the z direction. This direction rotation is the positive one. Here you have seen the del v del x. Okay, there you have seen the del v del x. Here we will see this del u del z. So therefore omega dot x is del u del z, half is there, minus del w del x. So this is the positive, this is the negative. So del u del z, that means the linear element here will have a positive angular velocities, that is responsible for a change in the x component velocity with respect to z. Similarly with y direction, what will be this linear, that means about y, oh sorry, I have written sorry, omega dot x will be in yz plane. So this will be omega dot y, sorry. So this will be omega dot y, I am sorry, because this is the y direction. So I have taken x, y, z like that. So similarly omega dot x, that means this will be in the yz plane, obviously. So this will be the yz plane. So this will be simply the del w, that means rotation in this direction will be positive, which is responsible for change in the y direction, y component of velocity. Change in, this is the change in the w component of velocity with y, del w del y minus del v del z. So this you can make it. I am sorry, because it is just haphazard x, y, z. So omega dot x, this is omega dot y, this is omega dot z. So this is the angular velocities or rotation x, y, z. That means this x, y, z means the rotation about z axis, rotation about x axis, rotation about y axis. So therefore we see the rotation is a vector which has got 3 distinct components x, y, z. So this vector can be written as half of curl of the velocity vector. You know this operator is known as curl. That means del operator in this and vector v. So if we write this, you will get the different components like this. Well, next definitely you know these things, that if you write this, what will be the term? Half I j k, curl operator is like that, del del x, del del y, del del z. This operator is I del del x, I j k are the unit vectors, j del del y plus k del del z. So if you make a cross product u, v, w, then from this determinant you can find out x, y, z component like that. That means these three components appear in this form, we can write in a vector form for the vector angular velocity, which has got three distinct components. This is your preliminary vector knowledge, you know. Now similarly in this case there will be angular deformation in three planes, one will be in xy plane. Here there is no problem because all are additive, del v, del x, del u, del y. So in xy plane the deformation is responsible for uv velocities and their dependence with xy. Similarly in xz plane it will be because of w and u, and this will be cross differential del u, del z plus del w, del x, xz plane. Similarly for yz plane, the deformation in the yz plane will be responsible for y component and z component of velocity, that means del w, del y plus del v, del z. So these are the three distinct components of deformation rates and three distinct components of angular velocities, in which case the angular velocity being a vector can be represented in a vector form like that. See, v bar is the velocity vector, v is the velocity vector, and having a component I u plus j v plus k w, I j k are the unit vector in x y z direction. We can write this curl, that means the cross product of del u with velocity vector v, which gives distinct components like that, omega x, omega y, omega z. Okay? Clear? No confusion? Now after this, please we come to an example. Let us come to an example. Please write, given an unsteady temperature field T, given an unsteady temperature field T is equal to xy plus z plus 3T Kelvin, and unsteady velocity field V like this, there is an unsteady velocity field like this. So what will be the rate of change of temperature of a particle at a point this at time t is equal to 2 seconds. So this is simply your application of the substantial derivative. Now in a flowing field, the rate of change of t dt del t dt, big T is the temperature in Kelvin. This is the function that t varies with x, y and z and time, and this is the velocity field, can be written as del t plus, you know that this is the temporal change, so this is the convective change, del t del x into del x del t, which is u. The way we derive, if we recall that change of any property in a flow which is convected in a flow field, so it should not be a velocity only, it may be a temperature. So its total change with time will be its temporal change with time, the temporal derivative and convective derivative. So a straightforward application. So what is del t here? The first term is 3. What will be u here? X, y. Now simply school level things. What is del t del x? Y. What is v? Z. What is del t del y? X. What is w? W is 3t. It is 3t. Oh, sorry, 5t. I am sorry, I have seen there. I am sorry. 5t. And what is del t del z? 1. So now this plus this plus this plus this is a function of x, y, z, t. So at this point and at this value of t and this value of x, y, z, now it's school level thing, you can find out what is the value of dt, dt. This is a simple straightforward application of using the concept of temporal and convective derivative to find out the total derivative. In case of time, it is the total change in time is this local change in time plus the change with convection. Okay, all right. Thank you for today.